For example, I'm going to place source here. This source is equal to something like unit load or something like that. I'm going to place a source here, concentrated load here. If this distance is L, so I'm going to place this source from something like R from here. This source is unit source. I'm going to call this point is xi1. So xi1 has a source load, something like unit load or something like that. So the effect at any point x, for example, if I have point here equal to x, this is just a general point, and x moves from x equal to 0 to x equal to L in the infinite beam. So the response at this point, I can write it like that. U at x equal to the effect of the source xi1, the effect, I'm going to say the effect of xi1, effect of xi1, okay, times the intensity of xi1. For example, if this source load is not equal to 1 to unity, so it is equal to 5, for example. This is the intensity at xi1, definitely. So U at any point x inside the beam or outside the beam equal to the effect of xi1 times phi at xi1, the intensity at xi1. If I place another source at any place, could be here, this direction, or could be this direction. For example, I'm going to take another xi here, xi2, separated from here by r also. So I'm going to make a summation and change this one to make it I and xi. So now I have the summation on xi1 and xi2 for the effect of xi times the intensity at xi. The effect of xi, this is the effect of unit source, of unit load, that in the infinite beam. That means I can solve this equation. EA times du, this is the effect, I'm going to give it x star by dx square, plus, instead of the load here, I'm going to put the Dirac delta. The Dirac delta at the point xi, and I leave it xi like this because I'm going to say it is xii. It could be xi1 or xi2. It doesn't matter where is the load. And this is equal to 0. As far as I point 2 points here, x and xi, so this u is not only dependent on x, it is dependent on x and xi. I'm going to give the same notation here. So it is a kernel now, it is not a function now. Okay? The solution of this equation is straightforward, is not a big problem. The solution of this equation, I can remove the EA direct and I use unit load instead of using delta. I'm going to use delta over EA. So directly I can say D2, actually this is the second derivative. So the integrate twice, one time, d by dx equal to minus 1/2 sine of x minus xi, and when we integrate the second time we will have u asterisk equal to minus 1/2 sine of x minus xi times x minus xi. And this is actually, this is the effect of unit source at xi. I can put it xi directly, is not a problem at all. It is a solution of infinite beam, a solution of infinite beam without any boundary conditions, because I didn't put any constants here. When I integrate twice the solution of the infinite beam, this is what we call it the fundamental solution. So I can write direct u of x equal sigma here times u asterisk of x minus xi I times the phi of xi I. And this is what we call it the indirect integral equation. It is not integral now. Actually, it is integral in one dimension. It is integral in one dimension because the summation here is over I, and here we have I equal 1, and here we have I equal 2, for example. Is that two boundaries. So what I'm going to do now, if I differentiate this equation, I'm going to differentiate this equation with respect to d by dx of point x, d by dx of point x, I will get the strain. Then I will multiply this strain by EA, and I will get the force, and I can write the force F of x equal to sigma over I sources EA times du asterisk of x minus xi I by dx times phi of xi I. Here, this is constant, phi of xi I is constant because we differentiate with respect to x, the coordinate of the x point. We do not differentiate with respect to xi, so xi now is constant. Because of that, here I use the partial derivative. I don't use the total derivative here. Okay, because these two sources are constant at their places. These two sources are constant at their places. The only moving part is the point x. The point x moves from here and here. It starts from x equals 0 and can move to any point here to x equal to L. These two integral equations, actually these are two integral equations. Mainly the summation here, this is integral actually. So the integral now is defined at 2 points, so we summate at these 2 points. This is very, very important. These are the two integral equations we have. These are the two integral equations we have, and these are the solution of the problem. We can define our problem in terms of these two new sources. So I'm going now to choose these two sources with different intensities, phi 1 and phi 2, to give me the same boundary conditions at these points. So if I choosing the intensity of the sources phi at xi1 and phi at xi2, for example, here is phi at xi1 and phi at xi2 is not unit any values to give me the same boundary conditions I have at these two boundaries. So at the end of the day, this will give me the solution for the problem. So now the solution of the problem is not defined in terms of integrations, and after we integrate twice, we got two constants and we apply boundary conditions to get these two constants. No, now we define the solution of the problem in terms of series, the effect of two sources. Why my choice, or why I choose in two sources? I choose in two sources mainly because I have two boundary conditions. Boundary condition here and boundary condition here. So I need two sources. If I have 4 boundary conditions, that means I need to choose 4 sources or something like that, and so on. Okay, but this is boundary value problem. The boundary value problem is defined in one dimension by two boundaries. So at each boundary we have prescribed value and we have unknown value. Okay,